Hello everyone. Today I want to share my work on learning generalizable network flow solver via neural networks. I'm Yize Chen, and I'm a final year PhD student from University of Washington. And this is a joint work with Ling Zhang and my advisor Baoseng Zhang. So let's get started from the background of the optimal power flow in power system and as well as a general power flow problem. So for this kind of problem, you have certain objectives. And in our case, it's just to minimize the power flow cost of the system. And at the same time, you have a lot of different set of constraints. For example, you have the flow balance for both problems. Well, for the optimal power flow problem, you also have a set of network constraints with regard to the physical law of electricity flows. So this kind of problem is really foundational. For example, in energy grid, the optimal power flow problem are running every 5 minutes to find the optimal dispatch of the generations from different generators. And due to the increasing complexity of the system, for example, there are many wind farms and also many uncertainties about the different scenarios. There is a need to solve the problem in a hard time constraint. But so here it has some space for the machine learning solvers as by using the conventional approach where you have the problem input and feed all the data into an optimization solver that may take a while to find the optimal dispatch solution. Well, in the machine learning algorithm, you can take a different step. For example, during training, you can use all the offline data to train the model to predict for the output solutions. While during testing phase, the inference from the input features to the optimal dispatch may take much smaller time compared to the optimization solvers. So by using machine learning, there may be some challenges. For example, the solution itself may not be that reliable, especially when you are considering this kind of very large physical system that may be violating the constraint. And in that sense, we may try to fine-tune solution from the neural networks, but we propose something different and trying to avoid all this kind of unreliability of the machine learning algorithm. And that is to say, we propose a different learning goals. And rather than just considering the end-to-end map from the input to the optimal dispatch, we consider a better design objective, which also can include more representation from the data and structure of the model itself. And also, in order to avoid the constraint violation problem, we propose approach that can decode the constraints by using the KKT optimality conditions of the underlying optimization model. And at the same time, our solution is straightforward from the neural networks, and there is no fine-tune steps. And the major takeaways from this kind of procedure is just to use the KKT conditions and use the knowledge from the optimization model itself to help the machine learning algorithm design. And our approach is centered around learning the optimal cost. And let's try to illustrate the DCOPR problem with some notations here. So basically, we want to find a group of dispatch that is a value of X and also satisfy a group of constraints where the generators has to be set within a certain bounds. And also the power flow has to be within the line flow limits. And there are the kind of balance on each bus, which is denoted in the last equality constraint. So the first kind of a choice is just to find the directly learning the solution for the optimal problem itself. And rather than considering the end-to-end approach, other alternative to say, how about learning the active constraints? And for this kind of DC approximation of the optimal power flow problem, there are actually p variables and there are p linear independent active constraints. And if you can learn this set of active constraints correctly, you can actually solve a group of linear systems rather than solving the original optimization problem. So in that sense, our approach is a kind of inspired by these two different approaches. And we propose a learning goal to learn the map from the load variations, which can be changed from time to time, that is L, to the optimal cost of the system, which also equals to the summation of the C transpose X. So this is a by itself is a supervised regression problem. And also by using this one, we just find that it's also not only learning the optimal cost, but it can give more information about the active constraint stuff. So we call this approach as a codebook because the KKT condition is just as a codebook and the neural network's gradient itself as a code words. So how does that happen? Essentially, what we have done here is just to take the derivative with respect to the neural network input once the neural network is trained during the training stage. And such gradient information are actually giving us the chance to find the optimal active constraints. And this is realized by just writing out the KKT equations and finding all the KKT conditions for the system. And so the gradient is actually the mu star value for the optimal dual variable associated with the equality constraints. And we can justify the value of the generations by either hitting the upper bound, lower bound, or within the bound by using the learned mu value here. And in economy, this can be also interpreted as a marginal cost of producing one more unit for the system, which is widely used in power system and electricity market. And in addition to using KKT conditions as a code word and code book, we are also using KKT conditions as regularizations during the training state. So in addition to the aforementioned supervised training loss, where we are using the neural network output compared to the optimal cost of the system, as well as the neural network derivatives with respect to the optimal dual value here, we also can add this group of unsupervised loss to the training stage, where we just explicitly write out all the KKT conditions and penalize the system training stage using the KKT conditions violations. And since this kind of function from the low to optimal cost, which can be proved is also a convex function, so we actually borrow from our previous work to use the convex neural networks to fit the function fitting procedures. So what we have done here is to use the KKT conditions as a code book to decode all the active constraints for the generators. And one more step is to identify all the active load flow constraints. And in that sense, we explicitly write out the dual problem, which can be decomposed to the problem associated with a dual variable associated with the line flow constraints. And in that sense, this problem can be transformed to a L1 minimization problem, which can be solved using complex sensing, which is a much faster and very efficient approach for solving the L1 minimization problem itself. So in this kind of, in summary, we propose a kind of approach by firstly find the gradients and then decode the generator states. And in the optimal power flow problem, we have one more step to decode the length constraints. While in the standard power flow problem, there is not that such step due to the constraints of the problem itself. And finally, with all the decoding active constraints, we can just write them together and just solve a linear equation solver. And all these steps are quite standard and take much smaller time than directly using optimization solvers. So this step also revolves to testing errors from the step one, since we have a key observation that for the linear programming problem, it can be actually divided into different polytopes. And in the same polytope, the active constraints are actually the same and the decision rules are the same. So as long as your prediction from the first step is not that far away from the correct values, you can always get the solution correctly. So in that sense, our problem revolves to this kind of learning errors. And during training, it's just a quite standard training procedure using a neural network. Well, during prediction, the only difference is just to take the derivatives and use the derivative information as the case steps for decoding all the constraints. And this procedure also has many properties, and one of them is just to say it can generalize well to different regions of the problem itself. So For an LP problem, there are actually exponential regions of active constraints combination with regard to your number of variables. And there can be encountered problem like in certain region, you don't have enough training sample, while in some regions, you even encounter this kind of sample during the training process. So recall that for this kind of problem, the optimal cost is actually a convex function over your input, which is the load variations. And the challenge here is to say, for the tested sample from the same regions of training sample, are we using the neural network? Can we learn this one accurately? And to make the problem a little bit more easy to understand, we just show, for example, if there are two training points, you learn the correct function, which can be denoted as the red line here. And once you have learned this function correctly, but during these 2 points, there can be many possibilities. So can we use the information from the convex neural network to solve this problem? And the second challenge to say, there may be some regions, there are not any training data at all. So in that sense, you have this kind of answer regions. So what will happen in the answer regions is also very interesting. And if the neural network-based optimization solver can recover the solution to a certain extent for the answering regions, that would be really great for this kind of proposed machine learning solvers. So for the first case about the testing data in the same regions of training data, and the intuitives, let's just follow this kind of intuitive example for the linear case, the piecewise linear function with only one line here. And if it is a convex neural network, you have to learn the correct gradients at the 2 points. And at the same time, since it's a convex function, so the only possibility is just the red line, and there's no chance to learn the green lines here. So in that sense, this kind of convex neural network can learn to generalize to this kind of compiled regions within the training sample. And we give the informal theorem here, which just say for the same LP region in the training and testing samples, as long as the testing sample is within the convex hull of all the training samples, you can guarantee the learned mu value is correct. And the second case is for the testing point from answering region. And in that example, the complexity also helps in the sense that since you know the gradients of the kind of backline here, so it's kind of constraining the slope in the middle regions. And in that sense, the learned gradients can just still help decode active constraints considering the robustness of the system. And this gets to the theorem 2 of our procedure, as you see, for the unseen testing points, as long as it's within the convex hull of training data, the learned mu is just a content in a bounding convex polytope. And for the simulation part, we just test our algorithm and compare with other algorithms in the terms of binding constraints, prediction, and the feasibility of the solution, and also the solution optimality ratio, and also the computation time compared to conventional solvers. And we compare to the end-to-end approach classification, nearest neighbor, and here's our result. So basically, if the load variation is not very large, our approach is comparable to the end-to-end approach. But if there is large variation over the input, where there are many different regions for the LP problem, so our approach can perform much better than the end-to-end approach. And also for a test of the generalization case, we just construct such example on learning a kind of unseen region of R1 using trained data from R0 up to R3. And magically, we found that for the testing samples on R1, our approach can learn with much higher optimality and feasibility ratio compared to the end-to-end approach. And also, if we add the system with some helper data, that is to say we do not know the optimal cost, but we use unsupervised learning that also boosts the system quite a bit. So essentially, we are in this work, we encode the structural information into learning to optimize procedure, and our case can be generalized to unseen cases. And there is also another talk trying to get more detailed work on the learning to solve optimal path flow problem. And for future direction, we try to explore the solution for the nonlinear and non-convex cases, as well as robust or stochastic formulation for the problem. And here is a paper reference, and if you're interested, and here is also the code repo here. And if you have any question, please don't hesitate to contact me. Thanks.